We learn to listen to space. It hasn't stopped singing. I like openings that feel like a breath, simple at first, then quietly profound. A decade ago, we built instruments so sensitive they could feel the universe shiver. Not with eyes and mirrors, but with lasers and silence. Since then, the sky has been full of music, brief rising notes from colliding black holes, longer murmurs from spiraling neutron stars, a choir of motions stitched into the fabric of space and time. Tonight, I want to sit with that music and trace what 10 years of listening have taught us, how the sound began, how it has grown richer, and why it matters that our species now hears the universe as well as sees it. Why speak now? Because the current campaign of listening, what we call Observing Run 4, has been the most abundant to date and is nearing its close. The latest plan from the collaboration sets the end of this phase in mid-November of the year 2025, after which the instruments will rest for upgrades. That schedule reflects a deliberate extension to deepen the run's scientific harvest. Earlier in the year, the network quietly crossed a milestone, the 200th gravitational wave candidate of this run alone, a marker of how routine, yet still astonishing, these detections have become. There was even a planned pause in the spring to retune and commission a sign not of faltering but of a mature observatory, making its tools sharper before returning to the sky. A decade is not long in astronomy, but what a decade it has been. On a September morning in the year 2015, two laser interferometers, one in Washington state, one in Louisiana, felt a tiny rising tremor. Less than a second long, it rose from low to high like a bird's call. Two black holes had spiraled together and merged more than 1 billion years ago. The ripple reached us that day. When we announced the result the following February, a century-old prediction stepped off the chalkboard and into the world, and gravitational wave astronomy began. From that first note to now, the score has thickened. By the end of the third observing campaign, the era we label 1 through 3, the published catalogue contained around 90 confident signals from compact binaries. The pattern was already clear. Stellar mass black holes are not rare curiosities, but common outcomes of massive stars, and the universe choreographs their mergers far more often than we had dared to hope. Observing Run 4 has since transformed novelty into rhythm, issuing well over 200 candidates in real time, and reminding us that somewhere, almost always, two collapsed stars are completing their final dance. What exactly are we hearing? Light tells us about surfaces, glowing gas, thunderous jets, the bright skins of stars. Gravitational waves tell us about motion itself. They are not emitted from a surface, they are woven by changing mass and energy as orbits tighten and horizons form. When two black holes circle one another, they stir space-time's geometry. When they collide, the newborn horizon rings like a bell and then settles. It is that ring and the approach to it that our instruments feel. To do so, the Laser Interferometer Gravitational Wave Observatory and its European and Japanese partners had to measure changes in mirror separations smaller than a proton's width, across arms kilometers long, and to do it through earthquakes, wind and human activity. That we can hear it all is a technical miracle. That we now hear often is a cultural one because it means we chose to invest in curiosity and patience. The listening is a partnership. In the United States, the twin detectors of the Laser Interferometer Gravitational Wave Observatory work in concert with the European Virgo Interferometer near Pisa and the Japanese Kamioka Gravitational Wave Detector in the Hida Mountains. Together, this LIGO-Virgo-Kagra network triangulates the sky better than any one instrument could alone, refines source properties, and increases the time we spend on sky at the highest sensitivity. Observing Run 4 began in late May of the year. 2023 has included strategic maintenance breaks and upgrades, and by the most recent, plan concludes in mid-November of this year with further improvements to follow before the next campaign. There is a human rhythm to this as well. We do not simply detect and tally, we share alerts within minutes. We revise as calibrations improve, and when an initial candidate fails more careful scrutiny, we retract with the same transparency. That is how a field grows honest, as well as fast. Over time, the raw stream of candidates becomes a carefully vetted catalogue, and that catalogue becomes a population black holes of surprising mass and spin neutron stars in rare partnerships, and the first hints of how environments shape their lives. The third catalogue gave us our first true census. The fourth run promises not just to swell the numbers, but to sharpen the questions: how do heavy black holes form in the first place? What role do star clusters and galactic nuclei play? And how often do neutron stars merge with one another, compared with their darker cousins? If this sounds almost musical, that is on purpose. The signals themselves are melodies, their shapes set by general relativity's simple, stern rules. We test those rules with every loud event, especially in the final ringdown, when a fresh horizon sheds its overtones and settles into quiet. So far, the theory holds beautifully, but the point of listening is to be surprised. A small deviation in the harmony could be a hint of new physics, an alternative gravity, an exotic compact object, or a whisper from the early universe. The discipline lies in hearing both the expected and the unexpected with the same care. Here is how I want to journey through this story with you. First, we will sit with that original tremor from September the 14th and feel how a single second of sound changed our ambitions for astronomy. Then we will widen out to the instruments themselves, the mirrors, the lasers, the control systems, and the human ingenuity that makes them sing together. From there we will turn to the harvest, what the catalogues tell us about black holes and neutron stars as populations, and how observing Run 4 has deepened, and in some cases changed the picture. Finally, we will look forward upgrades on the horizon, new facilities, and the dream of hearing fainter, slower songs, the rumble of supermassive black holes, and the background hum of the cosmos. And because a decade of listening is really a decade of becoming fluent, let us begin with the first syllable. We truly understood the rising chirp that arrived on Earth in the year 2015 and taught us that space and time are not silent. In the next part, I'll stand inside that moment and trace how a tiny ripple became a language. That first syllable arrived just before sunrise on a Monday in September, the year 2015. In the control rooms in Washington State and in Louisiana, two quiet corridors of vacuum and mirrors felt a rising shiver, soft at first, then bright as if someone drew a finger along the rim of a crystal glass. It lasted less than the span of a single breath. By the time the screen settled, the two laser interferometers, twin instruments of the Laser Interferometer Gravitational-Wave Observatory, had traced the same curve separated by a continent, yet in perfect sympathy. A ripple in the geometry of space and time had passed through Earth. It was the first time we had truly heard the universe. I remember the shape because it was musical. It began low and slow, climbed steadily, and ended with a brief, bright flourish, the chirp that had lived for a century in textbooks and simulations. We would learn that two black holes had circled one another for eons, drawing closer as they bled energy into space-time, until in a final rush they merged and rang down to quiet. That little arch on our screens was not light from a surface. It was motion itself encoded in the changing curvature of the universe. When we later stood before cameras in February of the following year to share the result, it felt less like an announcement and more like opening a door that had always been there. The parameters read like an epic written small. One of the pair weighed in at roughly 36 times the mass of our Sun, the other at roughly 29. Together they forged a remnant of about 62 solar masses. The difference, about 3 suns worth, flashed away as gravitational wave energy during that blink of a second. The source lay more than 1 billion light-years distant. Every piece of it, the slow sweep upward in frequency, the final whoop, the dying overtones as the newborn horizon settled, was exactly the melody general relativity told us to expect. That agreement is not just aesthetic. It is how we knew we were hearing, what we thought we were hearing. To appreciate the delicacy of that moment, imagine what had to be true on Earth. The instruments measure changes in length far smaller than a proton, across arms kilometers long. They must ignore earthquakes and ocean waves passing trucks and the whisper of air. All of that chaos had to fade enough just then for two facilities, thousands of kilometers apart, to trace the same rising line. The coincidence in time, the match in shape, the consistency with a relativistic binary, all of it came together not as a single proof, but as a braided rope of evidence that you could lean your weight on. When the paper appeared, Observation of Gravitational Waves from a Binary Black Hole Merger, it carried a simple sentence that still feels momentous. This was the first direct detection of gravitational waves and the first observation of a binary black hole merger. I sometimes think about the quiet that followed, not in the data which kept churning, but in the rooms where people who had worked for decades finally let themselves breathe. It is easy to forget that before that morning, black hole binaries of that mass were expectations, not certainties. The detection told us they exist, that they merge within the age of the universe, and that the cosmos is in some neighborhoods far busier in the dark than we had dared to hope. On that day, a century-old prediction stepped cleanly from mathematics into experiment. A field found its first unambiguous note. It would not be the last. What did the world learn? First, that general relativity speaks in melodies we can now record. Second, that gravity, this most familiar force, carries information we cannot acquire from light alone. Photons tell us about surfaces, about fire and skins and atmospheres. Gravitational waves tell us about movement, about mass in motion when there is no surface to glow. In that sense, the signal from September was intimate. We did not see an afterglow. We held the dance steps themselves. And third, we learned that our ears work. The twin observatories registered the same pattern within milliseconds of one another. The analysis pipelines developed over years recognized the template, the calibration held, and the consortium moved carefully and conservatively from excitement to certainty. In February, we told the world, the door once open stayed open. Soon after, more notes followed. Another black hole merger before the year's end. Then others, each with its own contour and key, each tightening our grasp on masses and spins, formation channels and rates. Within a few years, our colleagues in Europe joined with their detector near Pisa, and a detector in the mountains of Japan came online, turning a pair of listening posts into a network, a proper gravitational wave observatory. With triangulation came sharper positions on the sky. With additional baselines came better measurements of the sources themselves. The field was no longer a single remarkable event, it was an observing program. That is why the present season, the fourth observing run, feels like a symphony compared with our first solo. The collaboration recently celebrated surpassing 200 public candidates in this run alone, a visible sign of how routine the once unimaginable has become. And the schedule itself tells you we are treating listening as a craft plan pauses for maintenance and commissioning, extensions to overlap with new eyes on the sky, a clearly marked end date in mid-November of this year before we retune the instruments again. A decade on, we are not merely demonstrating that the universe sings, we are learning to conduct our time with it. But before we race ahead to catalogues and populations, I want to dwell just a little longer with the instrument that makes a whisper audible. What are these mirrors and lasers actually doing when they hear a wave? How do you float a mirror so that Earth cannot touch it? Hold a beam steady enough to notice a change smaller than anything we can see, and keep the whole contraption, the quiet, while the planet hums. If the first detection was our first word in a new language, the interferometer is the alphabet that lets us speak it again and again. So come closer in the next stretch. I'll walk you along an arm of the observatory from vacuum tubes to test masses and show you how we turned light into ears. I promised a walk along the arm of the observatory, so come with me. Quiet shoes, slow steps. A gravitational wave detector is at heart, a Michelson interferometer with two long evacuated corridors joined at a beam splitter. We take a single, exquisitely stable laser and send its light down both arms. When the beams return, they recombine. In perfect stillness, they cancel at the photodetector, dark as a closed eyelid. But when a ripple of space-time passes, one arm stretches while the other squeezes, the cancellation fails by a hair's breadth and a whisper of light reaches the sensor. That is the note we record. To make that whisper audible, we reshape the simple Michelson into a cathedral of optics, a power recycling mirror to flood the instrument with circulating light, and Fabry-Perot cavities in each arm to fold the path upon itself again, and again making kilometers behave like many more. The mirrors that do this work hang as if asleep. Each test mass polished, coated and heavy hangs at the end of a four-stage or quadruple pendulum. The goal is to let the mirror float free of the Earth's fidgets, filtering the planet's tremors away step by step. Even that is not enough, so the whole suspension is mounted on active seismic isolation platforms that sense and cancel motion in real time. You build silence in layers, pendulum isolation control, until the mirror is as close to freely falling as we can make it. Only then will it trace the passing wave. We house this stillness in one of the largest ultra-high vacuums on Earth. The two arms, each roughly 4 kilometers, are stainless steel beam tubes kept at pressures around a trillionth of atmospheric sea level. That emptiness matters. Air molecules scatter light. Outgassing can shake optics. Even a hint of condensation becomes weather. So we keep the corridors clean of almost everything. There's a fact I love: if you laid the vacuum volume end to end, you'd count tens of millions of liters held at that near-nothing pressure, with more than 100 million kilograms of atmospheric weight held at bay by steel, and engineering all so that light can cross without being jostled. It is a kind of secular sanctuary built for photons. Then there is the artistry. You cannot see the mirror coatings. A gravitational wave detector is limited in part by the thermal jiggle of those coatings, the tiny Brownian dance of atoms in the multi-layers that make a mirror reflect. Over the past few years, we have learned to lower that noise with clever materials, silica, paired with titania-doped tantalum, and in newer studies, titanium mixed with germania annealed to reduce loss. It sounds like alchemy, but it's careful materials. Science layer by layer, we trade a little optical absorption for much lower mechanical loss, and the instrument grows quieter without changing a single line in Einstein's equations. even after you tame the ground and the glass quantum mechanics remains. Light itself is noisy. The random arrival of photons, shot noise, limits our hearing at high pitch, while the back action of those photons, radiation pressure, pushes on the mirrors and spoils our hearing at low pitch. The modern trick is to squeeze the quantum vacuum, shaping its fluctuations so that the noise is reduced where it matters most. In the third observing campaign, we used frequency-independent squeezing. In this fourth run, we added a long filter cavity hundreds of meters to rotate the squeezing with frequency. The result is broadband quiet, several decibels of quantum noise reduction across the band, and the deepest ranges the instruments have ever achieved. It is a lovely thing to make quantum uncertainty itself lean out of your way. None of this works without trust in the ruler. The raw voltage at the photodiode must be calibrated into a dimensionless strain how much the arm was stretched compared with its length. We test and retest that mapping. A photon calibrator shines a controlled auxiliary laser on a mirror and uses radiation pressure to nudge it by a known amount. More recently, a Newtonian calibrator swings a calibrated mass nearby to tug the mirror gravitationally. If the instrument reports what we did to it, we believe what the universe does to it. That chain of trust from photon or tug to strain is what lets us turn a blip on a screen into the mass and spin of colliding remnants half a cosmos away. I should say a word about our partners because the network is the observatory. In Italy near Pisa, the European antenna contributes a crucial baseline. In the mountains of Kamioka, Japan, a detector built underground and cooled toward cryogenic temperatures, points to a future in which seismic and thermal noise are pushed even further down. The Japanese team's sapphire mirrors, chilled hundreds of degrees below zero, are an audacious bet that colder is quieter. Being underground, hundreds of meters of rock mute the Earth's constant shuffle. Each site brings a different genius. Together they let us triangulate the sky and cross-check our ears. When you add these ingredients, the recycled light, the arm cavities, the pendulums and isolation, the vast vacuum, the low-loss coatings, the squeezed quantum states, the careful calibration you get, not a gadget, but an instrument in the musical sense, something tuned. In this fourth observing run with its resumed C phase and upgraded optics, the tuning has paid off. Sensitivity curves have dropped, ranges have grown, the loudest events ring with overtones we can trace. The quietest on the edge of hearing still tip the balance toward discovery. And because the listening is now truly global, an interesting candidate seen in one place can be weighed and placed on the sky by many. It is in every sense an orchestra. I like to imagine the path a single photon takes on a good night. It slips through the power recycling mirror, splits, bounces back and forth along the arm cavities, perhaps hundreds of times, meets its twin at the beam splitter, and if space-time was perfectly calm, vanishes into darkness. But space-time is not calm. Somewhere far away, two massive remnants are circling, and that faint rising tide makes the darkness imperfect, just long enough for a few photons to land on the detector. From those few, we infer that a new black hole exists, or that two neutron stars have embraced, and we add another bar to the score. Now that we've walked the corridor and heard how light becomes ears, let's step back out under the night sky and listen to what those ears have told us about the creatures of gravity, the populations of black holes and neutron stars that the catalogues now reveal, and the surprises this fourth run has added to the tale. Out under the night again, we can hear not just single notes, but patterns, populations. After a decade, the catalogue has grown from a handful of extraordinary detections to a choir rich enough to study like an ecosystem. In the first three observing campaigns, our published census already sketched the outlines black hole binaries dominate. Neutron star pairs exist, and when they merge, they speak across the spectrum. And rare couplings of a neutron star with a black hole are real. Those early population inferences showed a black hole mass distribution with characteristic peaks, one near 10 solar masses and another around the mid-30s, and mostly modest spins a clue that many binaries may have lived quiet, isolated lives before their final dance. That was our opening map. Observing Run 4 has deepened that map and in places redrawn it. Midway through the run, the collaboration publicly celebrated, surpassing 200 significant low-latency alerts candidates good enough to share in real time with astronomers, an unmistakable sign that detections have become routine. By late August this year, the team noted that across all four runs, we have shared more than 300 public alerts, with the stream still flowing as the run approaches its planned conclusion in mid-November. The point is not the raw tally, it is the statistical power that comes with it. Once you have hundreds of voices, you can test how often heavy systems occur, whether spins tend to align or tangle, and whether there are truly gaps in the mass spectrum where stellar evolution forbids black holes to form in one step. About those gaps, theory has long predicted a pair instability desert for certain very massive stellar cores. Electron-positron pairs soften the pressure support, trigger runaway burning, and explode the star so violently that a black hole above roughly the 100 to 100 and a bit solar mass range should not form directly. Yet we have now heard mergers whose components stray toward, and in some cases, into that forbidden country. Fresh analyses this autumn, using the expanded catalogue from this run, find strong evidence for the lower edge of that gap and suggest that two distinct tribes of black holes may be present: a low-spin group consistent with direct stellar collapse and a high-spin, more isotropic group that likely grew through hierarchical mergers in star clusters black holes, begetting black holes. That picture is still sharpening, but it is exactly the kind of clarity you earn when the choir gets large. There have even been candidates massive enough to intrigue anyone who cares about the middle weight class, the so-called intermediate mass black holes that sit between the stellar kind and the supermassive giants in galactic goddess. Over the summer, collaboration members presented a record-setting conference stage result, a merger yielding a remnant in the few hundred solar mass range, with components likely in or near the pair instability desert and spinning rapidly. Independent teams have floated hierarchical merger scenarios to explain such extremes. These claims are correctly cautious, conference talks and preprints, first careful papers to follow. But they illustrate the new frontier. Once you hear often enough, you start catching the rare, and the rare teaches you how black holes grow. Spins too carry gossip from a system's past. In the early catalogues, the effective spin, a weighted average of the component spins along the orbital axis, clustered near zero for many events. That tended to favour formation in relative isolation, where supernova kicks and stellar winds leave spins small or misaligned. With this run population, studies are beginning to resolve subgroups, some events with appreciable, even extreme spins hard to get from first-generation stellar collapse, hinting at the churn of dense clusters where previous merger remnants become partners again. When you hear alignment, you suspect a tidy stellar binary. When you hear isotropy and high spin, you suspect the bustling dance floor of a cluster. The emerging split quiet collapses on one side, hierarchical builders on the other, feels like astronomy turning into social history. And what of the lighter voices? Neutron star pairs remain precious in number but priceless in what they tell us. The archetype is still the event from August of the year 2017, when two neutron stars merged, and the universe answered in light as well as in gravitational waves. A short gamma ray burst within a couple of seconds, a kilonova blooming across ultraviolet, optical and infrared bands, radio afterglow tracing an off-axis jet. That one moment stitched together theories about our process elements, jet structure, and the speed of gravity itself. Each subsequent candidate in that mass range raises the same hope. Can we find the glow map, the ejector, weigh the neutron star equation of state a little more precisely? The very reason this current run was extended into November is to overlap with new electromagnetic facilities, most notably the Rubin Observatory's early operations, so that when the next nearby neutron star pair sings, more eyes are open to watch the light. The ledger matters here with hundreds of black hole mergers and a much smaller but growing handful of neutron star systems. We can begin to speak in rates with confidence. The collaboration's public alerts guide now quotes expected detection rates translated from cosmic merger rates for each class, and those broad intervals are steadily narrowing as the catalogue expands. This is how a young field matures. You move from "we heard one" to "we hear them this often," and then to "they prefer these environments." Every new season shrinks the error bars and forces the theory to keep up. I love the humility that comes with this. For all our effort to make the instruments quieter, the universe keeps surprising us with louder, stranger stories, black holes that flirt with a theoretically forbidden mass range, spins that whisper of crowded nurseries, and still the occasional long, delicate spiral of neutron stars that invites astronomers everywhere to point their telescopes and join the conversation. The fourth run has delivered not just quantity, but contrast. And contrast is what makes a portrait come alive. So the music now has harmonies we can name: direct collapse and hierarchical growth, common black hole unions and rare information, rich neutron, star embraces, a probable desert in the masses with wanderers that cross it by unusual roads. In the next stretch, I want to step from populations back to a single luminous archetype, the day the universe spoke in both waves and light, and show how that multi-messenger moment rewrote our expectations for every run since. We will stand briefly beside that galaxy in Hydra, watch the kilonova bloom and follow the jet as it turns toward us, because when gravity and light sing together, the score becomes a map. I promised we would stand beside the archetype the day gravity and light sang together, so let me take you back to the 17th of August, the year 2017. A long, delicate inspiral rose in pitch for roughly 100 seconds, and then, just after the merger time, a short burst of high-energy light arrived from orbit, delayed by about 1.7 seconds. The gravitational wave told us 2 neutron stars had embraced. The gamma rays told us a jet had been launched. Within hours, telescopes found the host galaxy, a lenticular system named NGC 4993 in the constellation Hydra. It was the first time our ears and our eyes agreed on the same cosmic event with such clarity, and it remains the template for what multi-messenger astronomy can be. What made that day feel almost miraculous was the choreography. The 2 laser interferometer gravitational wave observatory instruments, one in Washington State and one in Louisiana, registered the wave, and the European Virgo antenna near Pisa, Italy, provided the extra baseline that tightened the patch of sky. That modest triangle turned a vast search into a manageable one for optical observatories, and by the close of that first night, many of us were watching a new point of light bloom and redden. It even earned a human name in the catalogue's AT 2017 GFO, the archetypal kilonova. The synergy was the Lesson 3 interferometers sketched the where and the when. The satellites and telescopes filled in the how and the why. The glow itself told a deeper story. In the blue early hours, the source looked almost like an ordinary supernova, but quickly it slid into red and then into the infrared, as if embers were being banked beneath ash. That color change was the signature of newly forged heavy elements. Theorists have predicted that the debris from a neutron star merger, rich in neutrons, would power rapid neutron capture, what we call the R process, and that the resulting atoms, especially the lanthanides, would be so opaque that the light would redden and linger. The models met the sky. The universe had shown us where much of its gold, platinum, and rare earths are born. I remember the odd intimacy of that realization, that the metal on a finger or a circuit board might have begun as ash from a brief, brilliant blossom like this long before our sun existed. Then the radio voice joined in. For weeks, the radio and X-ray afterglow brightened, peaked months later, and then faded, a behavior that resisted simple models of a jet pointing directly at us. The decisive clue came from very long baseline interferometry radio imaging so sharp that across those months astronomers could watch the source shift position on the sky. It moved with superluminal speed in appearance, a classic hallmark of a narrow relativistic jet viewed off-axis. The picture that emerged was elegant, an initially wider cocoon expanding into the medium with a successfully launched, tightly collimated jet that became visible as it slowed and its beaming widened toward our line of sight. That single measurement, apparent motion faster than light, though of course not actually so, broke a theoretical stalemate and linked neutron star mergers cleanly to at least some short gamma ray bursts. From gravity's side, the event became a Swiss Army knife for physics. The time delay of roughly 1.7 seconds between the gravitational wave and the gamma rays over a journey of more than 100 million light years put an extraordinarily tight bound on any difference between the speeds of gravity and of light. In the inspiral, the deformability of the stars, how much they tidally stretched, imprinted itself on the waveform, giving the first direct constraints on the stiffness of neutron star matter, and thus on the equation of state of matter at nuclear densities. And because we could infer the distance from the gravitational signal itself, then combine that distance with the redshift of the host galaxy measured in light, we could make a first beautifully direct measurement of the cosmic expansion rate with what we call a standard siren. Each of these threads grew into its own literature, but they all began in that one coherent moment. There was a human choreography too. 70 observatories on 7 continents and in orbit responded radio dishes, optical telescopes, ultraviolet, X-ray, and gamma-ray instruments coordinating through rapid alerts and circulars. It is easy to celebrate the romance of first, but the craft here was as compelling as the discovery pipelines that moved from candidate to sky map in minutes, observatories with pre-planned scripts for tiling large error regions and teams ready to sift ordinary supernovae from something subtler and faster. The day worked because people had practiced for it. In the years since, that single archetype has acted like a lodestar. We have heard many more black hole mergers and a smaller, precious set of neutron star candidates. but we have not yet repeated the full splendor of that day at the same certainty. That is partly statistics, nearby well-placed events are rare, and partly logistics. You need enough ears on the sky to localize well and enough eyes ready to follow up quickly. This is precisely why the current observing Run 4 was extended into the late autumn of this year, overlapping with new wide-field facilities coming online, and maximizing the chance that when the next nearby neutron star pair sings, we will catch its light as well as its gravity. The point of the decade has been fluency. We now know the tune, and we have the orchestra to follow it. When I think back to that galaxy in Hydra, I also think forward. Standard sirens, the marriage of gravitational wave distances with redshifts in light, offer a way to chart cosmic expansion without the ladders of Cepheids and supernovae. With a larger sample, we can help arbitrate the present tension between early universe and late universe measurements of the Hubble constant using physics so clean it feels almost indecent. Dark sirens, where no counterpart is found, can still contribute statistically by cross-matching well-localized events with galaxy catalogs. Bright sirens like the event in 2017 give the most direct leverage. The difference now is scale. With hundreds of detections per run, the trick is no longer whether we can hear, but how well we can translate what we hear into a map of the cosmos. So that day, gravity first light, a heartbeat, later taught us what to hope for and how to prepare. It showed that neutron star unions make elements launch jets, test relativity, and measure the universe all in a single breath. It is the emblem on the wall of this young field. In the next stretch, I want to lean into that cartographer's promise and stay with the cosmology, how standard sirens work in practice, why the words distance and redshift are so powerful when they come from different messengers, and how a decade of listening turns into a new way of measuring the size and speed of the universe. I said we'd lean into cosmology, how a decade of listening lets us measure the size and speed of the universe. So let's start with the simple but beautiful idea behind it. A compact binary signal gives us its own distance. The way the note grows, how loud it arrives for a given shape, encodes a luminosity distance without ladders or candles. Bernard Schutz saw this long ago. If you can also learn the source's recession, its redshift from light, then distance plus redshift gives the Hubble constant the present expansion rate of the universe. The phrase we use is standard siren, the gravitational analog of a standard candle. It remains one of my favorite examples of physics turning music into a ruler. We proved the method in the late summer of the year 2017. Two neutron stars sang 100-second in spiral. Less than 2 seconds after coalescence, a short burst of gamma rays arrived. Within hours, telescopes found the host galaxy in Hydra. From gravity, we took the distance. From the host light, we took the redshift, and together they yielded the first direct ladder, independent measurement of the Hubble constant. It was not yet razor sharp that would take many sirens, but it was gloriously clean. One event, two messengers, a new way to draw the cosmos. Sometimes there is no glow to guide us. Black hole unions are dark in light, but they are not useless for cosmology. The trick then is statistical. You take the patch of sky from the interferometers and cross-match it with a deep galaxy catalogue. Every plausible host contributes its redshift, weighted by how compatible it is with the siren's distance and position. No single system settles the matter, but an ensemble of dark sirens pulls the Hubble constant into focus. The first demonstration used a binary black hole event, and the dark energy surveys galaxies. Since then, teams have refined the method with larger samples and better photometric redshifts. The point is not romance, it is accumulation. With enough dark sirens, statistics becomes a kind of light. Of course, the universe and our instruments complicate the song. In the waveform, there is a well-known entanglement between how far away a system is and how it is tipped with respect to us. A face-on binary looks louder than an edge-on one, so distance and inclination trade-off. Breaking that degeneracy takes either exquisite waveform detail or an electromagnetic counterpart that fixes geometry. This is where extended networks, higher-order modes, spin precession, and polarization information help. Even then, the cosmos adds its own blur, large-scale structure, weakly lenses the wave, magnifying or dimming the amplitude in a way that masquerades as a distance shift. At low redshift, the host's peculiar motion with respect to the Hubble flow also matters and must be corrected. None of these are showstoppers, but they are the honest nuisances that set the error bars we quote. Why does this matter so much right now? Because the cosmos has been arguing with itself about the pace of its expansion. If you infer the Hubble constant from the ripples in the cosmic microwave background, the afterglow of the hot early universe, you land near the high 60s in the usual units. If you climb the local distance ladder with Cepheid variables and type Ia supernovae, you stand closer to the low 70s. The difference is not a quibble over rounding, it is a persistent tension that has survived new data and scrutiny. Standard sirens offer a third, independent arbiter that shares neither the early universe assumptions of microwave background fits, nor the anchor calibrations of the local ladder. That independence is the treasure. The first bright siren gave a proof of principle, the next step is weight of numbers. Every additional neutron star merger with a secure host pulls the uncertainty down. Every well-localized dark siren with a deep catalogue adds its own quieter tug. Forecasts are easy to make and dangerous to promise, but the broad lesson is clear. Dozens of bright sirens or hundreds of dark ones move us from demonstration toward decision. Along the way, the method matures better calibration of the interferometer's amplitude, better modeling of inclination and higher order harmonics, better treatment of weak lensing scatter at higher redshift, and better maps of galaxies in the relevant volumes. Sirens are young, but they are growing up quickly. There is a subtle delight in the way distance and redshift come from different senses. Gravity gives you a geometric distance, light gives you a spectroscopic recession. When they agree, confidence blooms. When one day they disagree beyond honest uncertainty, that discord will be a clue perhaps to new physics in the early universe, perhaps to unrecognized systematics in one method or the other. The wider theoretical community is busy mapping possibilities from early dark energy episodes around recombination to evolving fields and more exotic ideas. But the sirens will have their say precisely because their assumptions are so spare. And there is reach beyond a single number. With enough events spread across cosmic time, standard sirens can probe not just the present expansion rate, but also the way that expansion changes, testing the cosmic curvature and eventually the dark energy equation of state with a messenger insensitive to dust metallicity and many of the astrophysical complexities that dog traditional candles. Weak lensing will loom larger as we listen deeper, but even there, clever joint analyses treating the lensing imprint as both noise and signal promise to squeeze more cosmology from the same waveforms. This is what I love about the field. The instrument improves, the catalogue thickens, and ideas that were footnotes in old reviews become tools in hand. So that is the cartographer's kit. Sirens bright and dark, inclination tamed by networks and modelling, lensing and peculiar motions accounted for. An independent road into the Hubble debate and beyond it into the geometry and substance of the universe. In the next stretch, I want to show you how we turn that kit from a single number pursuit into a broader atlas. How the same decade of listening lets us test the fabric of general relativity itself. Search for a background hum from countless unresolved sources and perhaps catch hints of physics older than any star. I said we'd turn the cartographer's kit into an atlas, so let's start by asking whether the score itself is Einstein's. With hundreds of compact binary notes now on the page, we can test general relativity not with a single trumpet blast, but with an orchestra. In practice, the collaboration runs a whole battery consistency between the in-spiral and the post-merger ring-down parameterized knob twisting of the waveform to look for deviations checks for non-Einsteinian dispersion as the wave travels, and even tests of the allowed polarizations of gravity. Through the third catalogue, these probes found no discord within our uncertainties. The signals sing general relativity's melody. That verdict has only grown firmer as new events from observing Run 4 are folded in. One of my favourite examples is almost literary Hawking's area law. In Einstein's theory, the total horizon area of black holes should never decrease. With the very first signal, the binary that merged in September of the year 2015, we could weigh the areas before and after and ask the question directly. The answer to high probability was yes. The final black hole's area exceeded the sum of the two parents. A half-century-old theorem stepped cleanly from chalkboard to measurement. Since then, louder events have let teams revisit the test with overtones in the ring-down tightening how sharply we can hear the nascent horizon settle. That ring down those dying tones after merger has become its own craft black hole spectroscopy. Each mode has a specific pitch and decay time set only by the mass and spin of the remnant in general relativity. Resolve more than one, and you can ask whether they all agree on the same mass and spin. If they do not, something is amiss with the Kerr portrait. Work over the past few years has shown how to catch not just the dominant tone, but also its overtones, letting us begin true spectroscopy with the loudest signals and paving the way for decisive tests as sensitivity improves. Propagation gives us another lever. If gravity's quanta had a tiny mass, or if space-time itself bent the rules at very high energies, the wave would disperse low notes, and high notes would arrive slightly out of step after a cosmological journey. Across many events, we can look for that systematic drift. The collaboration's formal tests of GR analyses encode this as modified dispersion parameters, and the bounds so far say the wavefront stays achingly faithful to light speed travel. The same suite of tests uses the neutron star in spiral from August of the year 2017 to constrain dipole radiation and other departures, again within our reach Einstein's equations hold. Even the handedness of the wave is on trial. General relativity permits only two tensor polarizations. Alternatives add scalar or vector modes that would tug the mirrors differently around the globe. Multi-detector events, especially when an electromagnetic counterpart pins the geometry, let us compare those patterns. Reanalyses of the 2017 neutron star merger, aided by its precisely known host galaxy and jet orientation, strongly favor pure tensor polarization over pure vector or pure scalar. Gravity so far shakes the universe in the way Einstein said it would. If single bright notes test the score locally, there is also the question of the background hum, the stochastic sea made by countless faint sources you will never resolve one by one. In the Laser Interferometer Gravitational-Wave Observatory band, searches through the third observing run have set strong upper limits on such an isotropic background and mapped anisotropic constraints on any directional excess. Those limits already bite into some models of astrophysical populations and early universe relics, and the fourth run's longer baselines and lower noise are aimed squarely at pushing them down. Step to much longer wavelengths, years-long waves instead of milliseconds, and a different instrument has just heard that hum outright. Pulsar timing arrays turn our galaxy into a detector by tracking the ticking of millisecond pulsars. In the year 2023, the North American Nanohertz Observatory for Gravitational Waves reported Hellings-Downs correlations across dozens of pulsars, the telltale angular pattern of a common all-sky background, exactly as general relativity predicts. European and international consortia reported consistent evidence and are now pooling data through the International Pulsar Timing Array. The simplest explanation is a chorus of supermassive black hole binaries in distant galaxies. It is the same music heard an octave, many octaves lower. Why care about a background we cannot point to? Because a hum remembers history. In the interferometer band, a detection would encode the integrated lives of stellar mass binaries and any exotic contributions, cosmic strings, phase transitions in the young universe, other relics dreamed up in careful theory. Current upper limits already limit some cosmic string scenarios. The pulsar detections are beginning to weigh how quickly the giant black holes in galactic cores pair up and merge. Between them, low-frequency and high-frequency backgrounds could become a kind of archaeology, reading not one event but an era. There is also the joy of looking where theory is playful. Some searches in this run have chased the continuous, nearly monochromatic whispers that would arise if ultralight bosons, new particles beyond the standard model, grew clouds round rapidly spinning black holes and radiated by superradiance. Others target long-lived remnants or alternative polarizations in specialized channels. Most of the time, we report upper limits and move on. Sometimes, as with vector boson hunts in the first part of this run, we set the best limits to date in new corners of parameter space. Negative results sound like silence, but in a field this young, they are really contours on a map that tell the next expedition where not to wander. All of this only works because we know what our ears are doing. Calibration is not a footnote. It is the spine that lets cosmology and fundamental tests stand up straight. That is why you will see careful technical papers during this run, correcting subtle calibration uncertainties and tracing how they flow into parameters. It is also why the observing run plan itself matters. We have a clear endpoint mid-November of the year 2025 for this C phase, after which the instruments step offline for upgrades that will buy us more quiet and more reach before the next campaign. We are not just listening, we are tuning. So the Atlas is taking shape local tests that keep vindicating Einstein, a growing web of limits that fence in speculative physics, an emerging low-frequency background that tells us how galaxies grow their giants, and perhaps soon a higher frequency hum that fills in the story of stellar remnants and the early universe. In the next stretch, I want to live with that background idea more fully, how you tease a sea of unresolved sources out of noise, what today's best limits already imply for cosmic strings and phase transitions, and why the end of this run is perfectly timed to hand the question to the next generation of detectors waiting in the wings. I promised we'd live with the background, the sea of faint waves you do not resolve one by one, but feel as a persistent hum, so let's wade in slowly. Imagine every distant compact binary. You will never individually catch every stellar core collapse, every speculative relic of the very young cosmos all playing at once. The result is not a melody, but whether a stochastic background. On Earth, we tease it out statistically by cross-correlating the outputs of separated interferometers and asking whether there is a common sky-wide signal hiding beneath their local noise. In practice, we weight that cross-correlation by the so-called overlap reduction function, the geometric factor that encodes how a given detector pair listens together, and then integrate across the band to build up confidence. That is the craft at the heart of a stochastic search. You do not hunt a single crest, you measure the sea. We summarize the background strength with a dimensionless energy density, the Greek letter omega of gravity waves, as a function of frequency. How much gravitational wave energy per logarithmic frequency interval compared with the total energy density needed to make a flat universe. After 3 observing campaigns, the collaboration reported no isotropic background and thus placed upper limits for a flat spectrum. The energy density was constrained to be below roughly 5.8 times 10 to the minus 9. For a power law like that expected from a superposition of compact binary inspirals, the limit at 25 Hz was roughly 3.4 times 10 to the minus 9. Those constraints were many-fold tighter than previous runs and sat within striking distance of some astrophysical predictions. Just as importantly, the same analysis checked for spurious correlated magnetic noise from Earth's Schumann resonances and found none sufficient to mimic a background. Of course, the sky is not perfectly uniform, so we also map direction. Anisotropic searches treat the background like a faint radio sky. Radiometer techniques look for power from specific directions, and spherical harmonic methods build full sky maps that would reveal hotspots. The first 3 runs yielded no detection there either, but delivered the first joint sky maps using the European detector alongside the 2 American sites, and set upper limits on directional energy density and on narrowband flux from interesting targets like the galactic center and famous remnants. Each of those methods runs on the same foundational idea correlation over time, but the product is a picture rather than a single number. Why is this hum so enthralling? Because it remembers eras we cannot otherwise reach. In the audio band of ground-based interferometers, the dominant expectation is an astrophysical background from the aggregate of stellar mass black hole and neutron star pairs, too faint or too far to pick out one by one. Detecting that wash would give a census of compact binaries across cosmic time, complementary to what we infer from individually resolved mergers. And if layered atop it we saw an excess with a distinct spectral shape, we might be hearing something more exotic, a network of cosmic strings, a first-order phase transition in the early universe, or other relic physics that left a ripple instead of a photon. The present upper limits already shave away easy versions of some string scenarios. For example, analyses of the 3rd run constrained the dimensionless string tension to less than a few times 10 to the minus 15. For certain loop models, an improvement by orders of magnitude over earlier bounds. The method's beauty is matched by its honesty about nuisances. 2 interferometers share the same planet, so they also share global electromagnetic murmurs, microseismic seasons, and other correlated mischief. Modern stochastic analyses explicitly budget for that, including Bayesian fits that allow for a correlated magnetic background while asking whether any residue remains that looks like gravity's own. That is how we keep faith with a measurement that is by design a whisper. We demonstrate that the Earth's chorus is accounted for before we ascribe a hum to the sky. While the audio band has not yet yielded a detection, the very long wavelength frontier just has. Pulsar timing arrays, which turn our Milky Way into a galaxy-sized detector by clocking millisecond pulsars, announced in the northern summer of the year 2023 that they had found the telltale angular correlation Hellings-Downs that marks a common gravitational wave background across the sky. The simplest and presently favored interpretation is a chorus of supermassive black hole binaries in distant galactic cores, singing at nanohertz frequencies over years-long cycles. Multiple consortia reported consistent evidence, and they now combine data through the International Pulsar Timing Array to sharpen the picture. It is the same music many octaves lower, and its arrival turns background science from aspiration to practice. There is a deep satisfaction in seeing the 2 regimes begin to speak to one another. Nanohertz detections weigh how quickly giant black holes pair and merge and how gas and stars shepherd that process. Audio band limits tightening with each run are fencing in the total contribution from the stellar mass population and from speculative early universe relics. Together in time, they will give us a spectrum of the universe's restless past, from the slowly rolling bass of galactic nuclei to the treble hiss of stellar remnants, and perhaps a signature from the first fractions of a second, if nature was kind enough to make one. That is why the search goes on even when the plot looks like an upper limit curve. The absence of a line is still a contour on our map. Let me be specific about what goes on means, because it shapes the rhythm of our days. The current fourth observing campaign, now in its C phase, was deliberately extended and is scheduled to conclude in mid-November of the year 2025. The point of that extension was not merely to collect more chirps, it was to deepen overlaps with major electromagnetic surveys coming online and to deliver longer baselines for precisely these background searches. When the run ends, the network will stand down for upgrades before the next campaign. In the background context that pause matters, calibration improves quantum noise, squeezing deepens, scattering is tamed, and with each increment the cross-correlation sees a little further into the sea. If you listen closely to the technical papers, you can hear the field learning to ask more refined questions of the hum. Analysts now publish not only isotropic limits but also directional maps, not only power, law bounds, but also models tailored to compact binary populations, not only tensor backgrounds, but also searches for alternative polarizations that would betray non-Einsteinian gravity. Even the treatment of systematics, how we propagate calibration uncertainty into the background posterior, how we identify and marginalize over correlated noise, has matured into a literature of its own. That is what happens when a community accepts that a null result today is the scaffolding for a discovery tomorrow, and tomorrow is not far away in detector years. The upgrades that follow this run, the so-called plus configurations, are aimed squarely at lowering quantum noise at high pitch and thermal noise in the mirror coatings at mid-band, exactly where stochastic sensitivity benefits. Beyond those, the next generation looms a pair of American interferometers, with arm lengths scaled by a factor of roughly 10 and a European underground triangle, with cryogenic optics to chase lower frequencies. Their design studies show order of magnitude gains in strain sensitivity, and crucially for backgrounds, the ability to reach well below the astrophysical foreground into the province where early universe signals might live. Even the space-based observatory planned for the next decade will join this story, listening in the millihertz and connecting supermassive black hole hums to the nanohertz chorus below and the audio band above. The point is continuity. We are shaping a spectrum, not just a catalogue. So the C is in view. We have a method that turns two instruments into one ear, upper limits that already press on models of the young universe, and a complementary confirmed background at the longest wavelengths telling us how galaxies grow their giants. With the present run closing in November and upgrades to follow, this is the perfect hinge we can hand a sharpened question to detectors built precisely to answer it. In the next stretch, I want to step onto that near horizon, what the end of this campaign hands to the upgraded network, and what the coming observatories on Earth and in space will make possible when the universe's hum turns at last into the song we can name. The near horizon is wonderfully specific. We know when the present song will pause and when the instruments will be retuned. The Laser Interferometer Gravitational-Wave Observatory's fourth campaign, its C phase, is scheduled to conclude on Tuesday, the 18th of November, in the year 2025. After that date, the global network will stand down for upgrades until roughly mid-2026. The extension into November was intentional, a 6-week add-on to overlap with the first months of the Vera C. Rubin Observatory's early surveys, so that when gravity whispers, wide-field eyes can look at once. That is not just logistics, it is a philosophy of listening together. What then are we handing forward? First, a quieter pair of American interferometers already transformed by their plus upgrades. Frequency-dependent squeezing made possible by a 300-meter filter cavity at each site has trimmed quantum noise across the band. New core optics, better controls and lower loss paths for the squeezed vacuum have pushed the instruments to their best ranges yet, with broadband quantum noise reduction measured at several decibels in both Hanford and Livingston. This is the prosaic magic of the field. No new law of nature, just cleaner glass, cleverer light, and steadier hands enough to hear farther. Across the ocean, our partners each refine a different strength. The European antenna near Pisa continues its own advanced plus path, while in the mountains of Kamioka, the Japanese detector cools sapphire mirrors toward cryogenic quiet under hundreds of meters of rock that hushes the Earth's low-frequency shuffle. Those two design choices, underground sighting and cold optics, are the signature of the next generation as well. We are learning instrument by instrument how to tame the planet's fidgets and the atom's thermal murmur. Beyond this present run lies a step change. In the United States, Cosmic Explorer sketches a pair of surface observatories with arms tens of kilometers long, one around 40 kilometers a second, around 20 seeking roughly an order of magnitude leap in strain. Sensitivity. The point of long arms is simple and profound. They scale the signal without amplifying most noise. Planning documents from the project and national reviews now place Cosmic Explorer as the recommended American path to the third generation, designed to operate alongside Europe's underground triangle and the space-based mission to come. If built as envisioned, it would hear the universe not just farther but earlier in each merger's approach, turning a few seconds of song into long, richly structured phrases. Europe's answer is the Einstein telescope, a triangular observatory carved underground with three sides, about 10 kilometers each, nesting multiple interferometers and cryogenic mirrors to chase the murmur below 10 Hz. Its pathfinders and technical papers read like drafts of a new-ear vacuum that stretch for tens of kilometers, mirrors chill to tens of Kelvin, and sites under study from the Eurasia-Meuse, Rhine to Sardinia, with a third candidate added in Saxony. The triangle is not only elegant geometry, it is practical, giving multiple baselines and polarization sensitivity within one facility. It is the shape you choose when you plan to listen for decades. And then there is space. The Laser Interferometer Space Antenna, 3 spacecraft flying in a triangle millions of kilometers on a side, was formally adopted by the European Space Agency in the year 2024 with NASA as a partner, and is now in hardware development toward a mid-2030-something launch. It will hear the slow music, the courtships of supermassive black holes, ultra-compact binaries in our galaxy, and the resonant gossip of the early universe at millihertz. I like to think of it as the bridge between the nanohertz background already glimpsed by pulsar timing and the audio band we ply on Earth, a way to connect the base of galactic cores to the treble of stellar remnants. None of this happens in isolation. The Rubin Observatory's early science windows, slated to open in the months around October of this year, are exactly why our present run lingers into November. Rapid alerts from Rubin, together with survey telescopes in the radio ultraviolet X-ray and gamma-ray bands, will make the next nearby neutron star embrace a joint performance. Gravity sets the tempo, light colours the stage. The choreography has been rehearsed since that day in Hydra. The orchestra now is larger. What will these upgrades and new ears buy us scientifically? Earlier warnings for binaries within reach so that telescopes can be on target before merger. Clearer ringdowns so that black hole spectroscopy, counting the overtones of a newborn horizon, becomes routine rather than rare. A truer census of spins and masses, especially in the awkward middleweight country where hierarchical growth is suspected. And with long baselines and quieter coatings, a cross-correlated push toward the stochastic background, first the astrophysical wash from distant unresolved binaries, perhaps one day a relic from the universe's first instance. The promise is not a single discovery but a change of tense from we detected to we monitor. It is tempting to treat this as a march of hardware, but it is also a culture. The observing run page that marks our calendar with exact days and hours is really a compact between communities, instrument scientists who carve out quiet analysts, who turn blips into parameters, and populations and observers across the spectrum who tile the sky when the alerts go out. The end of this run mid-November looks less like a stop than a held breath before the next phrase. The ears will rest, the score will be revised, the song will go on. So as we stand on this hinge, one run closing a brighter network and new observatories coming into view, let me turn gently from instruments back to the sky. Upgrades matter because of what they allow us to ask. In the next part, I want to live with those questions about origins and environments, about heavy black holes made by many marriages, about neutron star matter squeezed past nuclear density, and about whether the universe keeps a relic hum from its first fractions of a second that with these new ears we might finally learn to name. Origins first, then environments, because the catalogue only becomes a story when you ask where these unions are made. There are two broad roads to a black hole marriage. One is the quiet lane of isolated stellar binaries, two massive stars born together trading mass-shedding envelopes and collapsing into a pair of black holes that finally meet. The other is the crowded square of dynamics, dense clusters where strangers pair off through three-body encounters, and sometimes where yesterday's remnant returns as today's partner-building mass and spin in steps. By the end of the third catalogue, the statistics already lean toward both roads, a mass spectrum with structure and effective spins clustered near zero, for many systems natural for tidy isolated binaries, yet with outliers hinting at wilder nurseries. That was the draft map we drew from the first three observing runs. Observing Run 4 has sharpened that map and in places redrawn its borders. Fresh population studies built on the expanded release. This northern summer reports strong evidence for the onset of the pair instability desert, the theoretically forbidden band in the black hole mass distribution where extremely massive stellar cores explode rather than collapse, together with signs of two subpopulations, a low-spin tribe consistent with direct stellar collapse, and a high-spin, nearly isotropic tribe extending into and across the desert, just as you would expect if some black holes are second-generation products of earlier mergers. It is an emerging picture, but the weight of data points in that direction now. If you stand inside those busy nurseries for a moment, the physics feels almost theatrical. In a young or globular cluster, heavy objects sink to the center, trade partners harden through encounters and sometimes merge. Their remnants, now heavier and often faster spinning, can be thrown back into the dance to merge again. Rapid cluster evolution models and modern N-body tools show how repeated pairings naturally grow masses and tangle spin directions, exactly the signatures we are beginning to identify in the catalogue. There is another bustling venue, the accretion disks of active galactic nuclei. Inflows of gas around supermassive black holes act like conveyor belts and glue shepherding stellar mass black holes into the disk plane, damping their orbits and hastening encounters. There they can pair merge and pair again their spins, nudge toward alignment with the disk. Recent analyses that let the data choose a mixture of components, masses, spin magnitudes and tilt angles find support for just such a split personality in the population, with an aligned high-mass, high-spin component that fits an AGN origin alongside a quieter low-spin component from the field. On top of that, theorists have begun predicting and observers have begun hunting for optical or ultraviolet flares from mergers inside AGN, disks, tiny fireworks riding on a sea of gas. It is a wonderfully concrete way to turn a population inference into an electromagnetic test. The populations are not just numerology, they are biographies. When you hear aligned spins and a narrow mass range, you suspect an orderly life. Two massive stars born together surviving winds, common envelope phases and supernova kicks. When you hear isotropic spins and very heavy remnants, including wanderers in the pair instability desert, you suspect clubs and disks, places where gravity is gregarious and history runs in loops. With hundreds of detections now on the ledger, the field has finally earned the right to speak in that register. And the neutron stars, they are rarer in our catalogue, but each one is a physics lab. The way two neutron stars deform each other on the way in their tidal give imprints itself on the waveform. From that imprint, we measure a parameter that tells us how squishy neutron star matter is, and therefore how pressure rises with density in the cores of these extraordinary objects. Since the event in the year 2017, reviews and new analyses have turned that single idea, tidal deformability, into constraints on the equation of state that sit comfortably beside nuclear experiment results and X-ray timing. As the sample grows, the credible region for a canonical 1.4 solar mass star's deformability will shrink, and with it, the space of allowed microphysics. Even without a flash of light, gravity alone weighs the stiffness of matter beyond atomic nuclei. With light as well, we triangulate on the truth. It is tempting amid such richness to skip straight to the headline numbers. But I think the most beautiful change is subtler fluency. A decade ago, we spoke in singulars, one chirp, one standard siren, one multi-messenger day. Today, we speak in ensembles. We fold in priors on star formation histories and metallicities. We compare cluster channels to AGN disks to isolated binaries. We ask not only what was this event, but what do 100 of these say about the genealogy of black holes and the constitution of neutron stars? That turn from event to population is the mark of an observatory coming of age. And the implications flow outward. If high-spin, high-mass mergers truly trace crowded environments, then they are signposts to places where hierarchical growth could seed the middleweight class bridging stellar black holes and the behemoths in galactic cores. If low-spin binaries dominate in the field, then stellar winds, metallicity, and common envelopes become the levers that set the mass and spin budget of the universe's most common mergers. Meanwhile, every fresh neutron star in spiral inches the dense matter story forward. Symmetry, energy crust, thickness, threshold masses, for prompt collapse items that sound arcane, until you realize they govern how and where the heavy elements in our rings and circuits were minted. You can feel too how this decade of hearing changes what we hope to see. If some mergers truly happen inside AGN, DISC's coordinated campaigns can look for the promised thermal flares. If some black hole remnants are the children of earlier unions, we can search for their spins and masses to betray that ancestry. If neutron star pairs are caught early enough, we can lay out telescopes for a killer nova and measure its colors as a clock for element making. This is where the extended end to observing Run 4 pushed into mid-November to overlap with the first months of the Rubin Observatory's wide surveys begins to matter. More ears on the sky, more eyes ready to follow the hints that population work gives, all of which returns us to the craft. Populations are only as honest as the pipeline that finds and vets each note. In this run, alerts went public within minutes. Candidates were revised as calibration matured. Some were retracted with equal clarity when deeper checks failed to confirm them. Behind that cadence sits a machinery of low-latency searches, sky map production, and a public database where the whole world can watch the stream. In the next stretch, I want to step behind the curtain and walk you through that path from a whisper on a photodiode to a notice on astronomers' screens, because the way we listen together is as important as what we hear. Step behind the curtain with me then, from the whisper on a photodiode to the message that wakes an observatory on the far side of the world. In the control rooms, the raw light is turned into numbers and streamed to low-latency searches that never sleep. Several families of algorithms share the watch. For mergers, we expect black holes and neutron stars spiraling in. We use match filter pipelines such as GS, TL, AL, and Pi-C-BC Live, along with MBTA and SPI-IR. Each carries a bank of model waveforms and asks second by second whether the data look like any one of them. For signals, we do not wish to assume bursts of unknown shape. We keep a free-form ear tuned the coherent wave burst method, which looks for coherent excess power across the network and reconstructs a signal with wavelets when it finds one. All of these have been refined for the present observing run. Their performance in practice and rehearsal has been documented in careful technical papers over the past few seasons. When any of those searchers believes it has heard something interesting, it sends a trigger with its best guess of the time and a ranking. A central conductor, our event orchestrator called GW Celery, collects triggers from all pipelines and clusters neighbors in time into a single super event, our working proxy for one astrophysical thing. That super event and everything we attach to it lives in the GRACE database. GRACE-DB, a public-facing ledger with a unique identifier that encodes the date S plus the 2-digit year, month and day, followed by 3 letters. At any moment, one trigger is preferred inside the super event. The preference may change as better information arrives, but the super event is the thread that holds the story together. How interesting must a trigger be before the world hears about it? The Public Alerts Guide lays down thresholds. A preliminary alert may go out automatically when the implied false alarm rate sits around 2 per day, a permissive level meant to catch promising candidates early. Significant alerts, those we take as likely astrophysical, correspond to far rarer rates on the order of 1 per 7 months. For the compact binary searches, with slightly different yardsticks for special subsolar and for burst analyses, those numbers are not law, they are in writing and they shape the rhythm of our nights. The instant a super event is born, 2 further engines start to turn. First, rapid sky localization for compact binaries. We run Baystar, a lightning-fast Bayesian triangulation that ingests the timing, phase, and amplitude information from the search, and in seconds to tens of seconds returns a 3-dimensional probability map position on the sphere and distance that is usually good enough to point telescopes. For unmodeled bursts, Coherent Wave Burst provides its own rapid localization from the coherent reconstruction. Later, slower parameter estimation runs Bilby and rapid PE Rift for binaries. Bayeswave or LIL inference burst for bursts arrive with refined posteriors on masses, spins, distance, and sky. It is typical nowadays for a single event to carry an initial Baystar map, and many hours later a Bilby map that tightens the credible region and shifts the center by a little or a lot. Second, we compute a quick interpretable classification, the probabilities that the source is a binary neutron star, black hole pair, a binary black hole, or simply terrestrial noise. We also attach properties that answer practical questions. Does the system probably contain at least one neutron star? Is mass likely to be ejected? Could a component fall in the so-called mass gap? Is there any chance a component is subsolar? These fields has NS, has remnant, has mass gap, has SS, EMA, right there in the public notice schema because follow-up teams need them at a glance. The alert itself is a small marvel of plumbing. Once the super event passes the threshold, our infrastructure posts a notice to the community over Kafka streams run by the Gamma Ray Coordinates Network and the SCM-MAR Federation. Machine-readable messages use either JSON or Avro schema and include embedded a multi-order Helpix sky map, the efficient variable resolution format adopted because localizations are now sharp enough that single resolution maps would balloon in size. The same alert has a human twin, a GCN circular, that summarizes significance, localization and classification and points to the files on GraceDB, often including the literal file name baystar.multiorder.fits,0 and its successor, 1, followed later by bilby.multiorder.fits. A typical circular today even lists multiple gravitational wave-only maps distinguished by version count, a concrete sign of how a super event evolves as different pipelines take their turn. This evolves matters. Alerts arrive in stages, an early warning or a preliminary notice first, then an initial notice after human vetting, then updates as calibrations settle or as a slower analysis finishes, and sometimes honestly necessarily a retraction. When a candidate fails, the deeper checks. The Public Alerts Guide is explicit that a retraction is not a scandal, but a safeguard, and that the initial circular should be treated as the first citable statement of fact for an event. That clarity builds trust between those of us who listen in gravity and those who will spend precious time and weather to look in light. A special word about early warning. Binary neutron star inspirals linger in band for minutes. If they are near and loud, our pipelines can sometimes accumulate enough signal to noise to cry out tens of seconds before merger. In the present run, all the main compact binary searches GSTLA, LMBT, IPyCB, CLive and SPIIIR participate in this pre-merger model. The notices they issue are conservative about classification, assume binary neutron star or terrestrial, and their localization is at first coarse, tightening dramatically in the last breaths before coalescence. But even a minute's warning lets robotic telescopes find a patch of sky, open shutters, and hold their breath with us. If you peer carefully into the metadata, you can see the whole choreography encoded. The group is compact binary coalescence or burst. The pipeline is named GSTLALMBT IPyCB CSPIIIR coherent, wave burst and others. The significant flag uses a trials factored false alarm criterion. The multi-order sky map is base 64 encoded in a JSON alert. The GraceDB identifier, the S followed by a date, and letters ties all updates together. To a human, the circular is a sentence. To a machine, the Kafka message is a packet. To a field that lives on both sides, they are the same music written in two clefs. And because this is an observatory, not a black box, all of it is documented: how super events are built, how the orchestrator listens to GraceDB's pub subfeed, how latency accrues principally in three places: the search itself, the orchestrator's bookkeeping, and the database transactions. That transparency lets partners build their own listeners that act on our notices, running coincidence checks with gamma ray triggers, for instance, and it lets the public watch in real time as a candidate ripens, is revised, or is retired. From the outside, a gravitational wave alert can look like a single chime. From the inside, it is a small symphony matched filters and wavelets, a conductor that clusters and promotes a sky painter that works in seconds, and another that labors for hours, and a messenger that speaks both to humans and to machines. The point of learning this machinery is not to fall in love with plumbing, it is to remember that good listening is patient, layered, and honest about uncertainty. In the next part, I want to live through one night with you, trace a single candidate as it blossoms from a whisper to a map, feel the pause when the calibration team sends a caution, watch the circular go out and follow the telescopes as they tile the sky, because the life of a detection is really the life of a community deciding together what the universe has just tried to say. Picture a Tuesday night. The air is still in the control rooms, the lasers hum like quiet bees. Somewhere after midnight, the matched filter sentries stir. One of the compact binary pipelines, GSTLAL, the G-streamer, laser analysis, lifts a hand. Its template bank has found a curve in the data that looks like two compact objects spiraling together. A moment later, Pi-C-BC Live, another Guardian, confirms power at the same time. On a different screen, the multiband template analysis MBTI murmurs agreement. These are the watchkeepers that do the first pass in real time, tuned for speed without sacrificing too much subtlety. They have been rehearsed for this run on carefully staged mock data challenges and years of upgrades. The first act after any shout is to braid the shouts together. A small, steadfast program called GW Celery listens for triggers and gathers neighbors into what we call a super event. Our working thread for this is probably one astrophysical thing. It writes that thread into the Grace database, our public ledger, where the super event gets a date stamp name and a home that all later updates will use. Inside that thread, one trigger is preferred, but the identity can change as better information arrives. The super event is the story spine. At the very same moment, an engine for fast triangulation spins up. Baystar, the rapid Bayesian sky painter, swallows the timing, amplitude, and phase information seen across the network, and in something like seconds to tens of seconds, returns a three-dimensional localization, a probability pattern over the sky with a distance estimate folded in. It is not the last word, but it is a map fast enough to move telescopes. The beauty of Baystar is its speed. The patience comes later with the heavyweight samplers used by Bilby and friends. Now we must decide how loudly to speak. The public alerts guide sets two rungs. A permissive low significance threshold, false alarm rates around a handful per day, allows preliminary notices to flow automatically so that observers can be poised. A significant alert is rarer by design, with false alarm rates around 1 per month for compact binary searches and around 1 per year for unmodeled bursts. These get human vetting before they go. That two-tier rhythm is written down precisely because nights like this demand both speed and care. Suppose tonight's candidate passes the first rung. The machinery posts a machine-readable notice over the gamma-ray coordinates networks. Kafka streams JSON or Avro packets that include the sky map bytes directly, not just the link. The map is a multi-order HealPix file, an efficient variable resolution format we adopted so that rapid localizations could be small and faithful. The switch to multi-resolution fits was made explicit in the changelogs years ago, and it matters every night. A human-readable circular follows pointing to the same files on the Grace database and spelling out the early probabilities. Does it look like a binary black hole, a neutron star, black hole pair, or a double neutron star? How probable is terrestrial mischief? What distance does Baystar prefer? On this night, the classification fields carry their usual shorthand. Has NS, has remnant, has mass gap. Quick, interpretable numbers attached by trained classifiers designed to answer practical questions at a glance. Does at least one object likely contain neutron star? Matter is post, merger matter likely. Is there any chance one component sits between 3 and 5 solar masses, the so-called gap? These toggles are not folklore. They are documented right down to the schema, and in recent technical papers, to the machine learning methods used under the hood. If instead the candidate were an early warning case, a lingering nearby neutron star in spiral, our notices would say so. In that mode, the system assumes binary neutron star or terrestrial, sets the neutron star and remnant flags to full by construction, and ships a course map that tightens dramatically as the final minute ticks down. We rehearsed that style of public early warning during a post-third run technology demonstration, and for this fourth run, teams have worked to make the pre-merger path as conservative and as useful as possible. Even tens of seconds are enough for robotic telescopes to slew and be waiting. Back to tonight. The first Baystar map lands. Telescope schedulers wake and tile, prioritizing galaxies in the high probability swath. From here, the super event lives and breathes. A calibration team nudges the amplitude model. Baystar is rerun. The map shifts a little. Hours later, a slower parameter estimation job, Bilby say, completes its first pass, replacing the quick map with one that folds in more of the waveform structure and returns refined masses, spins and distance. This is expected. It is in the manuals and the literature. Baystar for seconds, Bilby for hours, a chain of increasingly incisive portraits. Inside the detection room, there is also the unmodeled ear-coherent wave burst, painting its own quick picture when the data show excess coherent power without asking for a specific compact binary shape. That method, based on wavelets and a coherent statistic across the whole network, has its own proud history, including the first black hole event in the second decade of this century. It runs in parallel, precisely so that our imagination does not limit our hearing. It is worth saying how the plumbing feels from the outside. To a follow-up team, The Life of the Night appears as a stream on Kafka first, a preliminary, then an initial, then updates with version 0 and version 1 of the Baystar map, then perhaps a Bilby replacement. Each notice contains the super event identifier date, plus letters that ties the story together. The Public Alerts Guide stresses that a retraction when it comes is an act of hygiene, not embarrassment. We would rather step back than waste the community's weather and time. Sometimes the night blooms. A gamma-ray satellite reports a short burst near the time of coalescence. A small telescope posts a transient in the preferred patch. Radio schedulers set a timed cadence. More often the night is quiet. The candidate resolves into a black hole union with no likely light, or it yields to a subtle artifact that fooled the first pass. The point of the observatory is not that every whisper becomes an aria, but that the score is kept honestly, thresholds written down, latencies measured and published, end-to-end performance tested in public analyses, so partners know what to expect when the phone rings. By dawn, tonight's thread has settled. The last circular summarizes the refined map and the source class. If it is a significant event, the vetting notes are embedded. If it is not, the super event still lives on the ledger for anyone to study. Somewhere else, the pipelines yawn and stretch and turn back to their quiet watch template banks and wavelets at the ready. And across the world, a dozen observatories have little rectangles on their sky from a night spent looking together. I wanted you to feel that cadence, the choreography from photodiode to telescope, from Baystar's seconds to Bilby's hours, from permissive preliminary to careful, significant, and to know that every part of it is written down and shared. Because an orchestra only sounds good when everyone can see the score. In the next stretch, I want to linger with the opposite nights, the ones that teach us humility, the near misses, the clever glitches, the correlated earthly murmurs we model and subtract, and the careful culture of retraction and revision that keeps us honest as we listen for the universe's next breath. Not every whisper is the universe. Some nights what looks like a song is Earth clearing its throat. We have names for these imposters: blips, koi fish, scattered light, scratchy little creatures on a spectrogram that mimic the curves we care about. They come from scattered photons motion in suspended optics, control loops, catching their breath, even lightning far away that shakes a sensor. Over the first few observing campaigns, we learned their habits and built a taxonomy. Blip glitches in particular were notorious for masquerading as short, chirpy mergers, while scattered light drew soft arches across time frequency maps when something in the beam path moved by a hair's breadth. Knowing their signatures and how they bias searches became part of the craft. We don't try to wish them away, we study them. A community project called Gravity-Spy married human pattern spotting with machine learning so that volunteers and algorithms could sort glitches into classes, giving analysts fast-labeled examples to build vetoes and to hunt the environmental channels that correlate with each beast. In this run, those classifiers have been upgraded again, fusing multiple views of the data so that a koi fish-like swoop is less likely to trip a compact binary search. It is not glamour, but it is what turns plumbing into an observatory. You catalogue the ways Earth pretends to be a black hole, and then you teach your pipelines not to be fooled. Even when two sites are quiet, a subtler mischief lurks the planet's own heartbeat. Global electromagnetic resonances in the cavity formed by Earth's surface and ionosphere, Schumann resonances, can produce low-frequency magnetic fields that are correlated between continents. If those fields couple into both detectors, they can masquerade as a shared skywide hum in stochastic background searches. For years we have instrumented the sites with magnetometers, measured the couplings and developed analyses that explicitly fit a correlated magnetic term alongside any putative gravitational background. The recent verdict is reassuring through the third rung. Correlated magnetic noise sat below the interferometer's sensitivity, but we keep modeling it because the next generation instruments will hear deeper, and complacency is not a friend. We also test ourselves by faking the sky. Hardware injections, true physical nudges to the mirrors, let us drill the entire chain from photon to paper. Drive an actuator with a waveform that looks like a binary in-spiral and watch the control system and searches respond. If the pipelines recover the event with the right parameters, confidence grows that a real wave would travel the same road. Once in the days before first discovery, we staged a blind injection, the infamous big dog, without telling the analysts. They found it celebrated, and only later did we open an envelope and confess it was a drill. It sounds mischievous. It was pedagogy. An observatory that can be fooled on purpose is an observatory ready to be convinced on principle. Still, humility is policy, not just posture. The Public Alerts Guide bakes it in 5 kinds of notices: early warning, preliminary initial update, and retraction and thresholds that trade speed for caution. A permissive preliminary alert can flow within minutes when a super event crosses the public false alarm threshold. Initial and later updates tighten the sky map and the classification as better calibration and slower parameter estimation results arrive. Retraction is a first-class citizen for nights when a candidate fails deeper checks. Even the file names carry that honesty. Multi-order sky maps are versioned explicitly baystar.fits, 0, then 1, so partners know the map changed beneath the same name. None of this is theatrical. It is how you keep trust when the business at hand is whispered. Let me give you the feel of a near miss. A burst of excess power crests in 2 detectors. Coherent wave burst sketches a patch on the sky. Baystar's first map is broad but enticing. Robotic telescopes spin up. Then a calibration specialist notices a suspect line in an auxiliary channel. A scattering model says a seismically induced arch may be bleeding into the strain. We rerun the localization with a refined calibration, and the patch slides. Parameter estimation hours later returns posteriors that are suddenly incompatible with any compact binary we consider plausible. A circular goes out with a retraction, and the GraceDB thread is closed. From the outside, it's a single tidy message. From the inside, it is a dozen people choosing accuracy over adrenaline. The measure of a maturing field is not only what it announces, but what it is willing to unannounce. Data quality is more than a yes or no, it is a web of vetoes. When a specific auxiliary channel, a microphone, a magnetometer, a suspension sensor shows a correlated disturbance, we can mark and remove that slice of data as unsafe for astrophysical inference. When a class of glitches is reliably identified, like a family of scattered light arches that erupt during windy hours, we can downweight or excise those times in low latency searches, and we can quantify how much sensitivity we gain by doing so. The dull words are veto evaluation. The lived experience is a detector that spends more of its night listening to the sky and less to its own bones. And then there is the background problem again, because near misses feed that too. Cross-correlation searches for a stochastic hum rise and fall on our ability to prove that whatever 2 sites share is celestial, not terrestrial. That is why the newest analyses fold correlated magnetic templates directly into the inference, asking the data to tell us jointly how much of the common power is Earth's and how much is the universe's. Most days the answer is not yet upper limits maps with no hotspots, but the method grows surer, and the next observing run will inherit a cleaner ear because we learn to listen through the planet, not around it. All of this can sound like housekeeping until you remember what it buys credibility. When we say a heavy, high-spin merger likely happened in a crowded nursery, when we hint that a kilonova might be blooming 200 million light-years away, when we report a sky-wide upper limit on a cosmic hum, we want you to hear not certainty but earned confidence. The confidence comes from knowing our failures, naming our glitches, practicing our drills, versioning our maps, and choosing retraction over romance when the evidence tilts. That to me is the quiet beauty of this decade. We learn to listen, and we learn to doubt what we heard just enough to make belief meaningful. With that culture in place of drills and vetoes, of magnetic monitors and machine-readable honesty, we are ready for the next questions to count. In the next stretch, I want to raise our eyes from the control room back to the sky's long arc to make sense of what 10 years of songs have changed. In our picture of the cosmos, how often stars die as pairs, how black holes grow families, how elements find their way into rings and circuits, and why the closing bars of this run feel less like an ending than like taking a deeper breath before the next phrase. Raise your eyes with me, not to a single night in the control room, but to the sweep of a decade, and feel what the songs have changed in our picture of the cosmos. The first change is scale. What began as a lone rising chirp is now a steady cadence. Through this 4th observing campaign, the collaboration has sent out well over 200 significant public alerts from this run alone, and across all 4 campaigns the tally of real-time notices now exceeds 300. That is not a press release flourish. It is the sound of gravitational waves becoming routine. No longer rare fireworks, but weather we can forecast and study. The schedule itself carries this confidence. The present sea phase is set to conclude on Tuesday, the 18th of November in the year 2025, an extension chosen so that our listening overlaps more deeply with wide field surveys as we hand the baton to the next upgrades. With numbers comes biography. The population paper that closed the first 3 campaigns taught us that black hole unions are common, that their masses cluster and then roam, and that many arrive with modest, often misaligned spins, hints of quiet lives in isolation, punctuated by wilder tales from crowded nurseries. Those inferences were not guesswork. They were carved from dozens upon dozens of events, weighted carefully and tested against bias. What this 4th run adds is contrast and confidence. The abundant detections sharpen the contours of the mass and spin distributions, and the outliers no longer look like curiosities, but like the leading edges of distinct subpopulations. Consider the theoretically forbidden country in the mass spectrum, the desert carved by pair instability in the most massive stellar cores. Classic theory predicts that above a certain threshold, a star's heart softens, burns, runs away, and tears itself apart, leaving no single-step black hole behind. Yet our catalogue now reaches toward and sometimes into that desert. Fresh analyses this year report strong evidence for the onset of the gap, and with it signs of a second tribe, heavier, higher spin remnants, whose properties look less like first-generation collapse and more like the children of earlier mergers. It is a portrait in which one pathway builds quietly from massive stars in binaries, while another pathway, hierarchical growth, stacks mass and spin in steps. The orchestra of detections is large enough now to separate those melodies. Where then do the wild ones grow up? Dense clusters have long been the favoured stage-heavy objects, sink to the centre, trade partners harden and sometimes merge more than once. But there is another theatre whose footlights have begun to brighten the disks of active galactic nuclei, the vast whirlpools of gas around supermassive black holes. Gas can shepherd stellar mass black holes into the disk plane, damp their orbits and help them pair and pair again. Analysis over the past few seasons have explored whether some of the most massive high-spin systems, and even a contentious flare spotted weeks after the famously heavy event in the year 2019, might carry the signature of mergers in such disks. The case is not closed. Caution is part of our craft. But as theory sharpens and datasets bloom, the idea that some black hole families are raised in gaseous cities is moving from speculation toward testable prediction. The lighter voices tell a different story, just as profound. Neutron star pairs remain fewer in our ledger, but each one is a physics laboratory. From the way they tidally deform one another in the in-spiral, we read the stiffness of matter beyond atomic nuclei. From any light they cast, we learn how the heaviest elements are forged. The archetype from the year 2017 remains a lodestar, a long in-spiral in gravity, a short gamma-ray flash 1.7 seconds later, and a kilonova that changed colour as newly minted elements thickened the light. In the years since, reviews and new modelling have strengthened the chain from waveform to equation of state, and from glow to nucleosynthesis. Strontium identified in early spectra lanthanide opacity, controlling the reddening mid-infrared embers pointing to truly heavy species. Piece by piece, the universe has shown us where much of its gold and platinum are born. Rates the quiet arithmetic of how often or where biography becomes demography. By the close of the 3rd catalogue, the collaboration could speak incredible intervals for how frequently black hole pairs, mixed black hole neutron star couples, and neutron star pairs merge in a cubic gigaparsec per year, and how those rates might evolve with redshift. The exact numbers are not lullaby material, but the message is these unions are common in a young universe and still frequent today, with black hole pairs the reliable baseline and neutron star pairs the rarer, information-rich solos. The 4th run, with its flood of candidates and richer parameter estimation, is tightening those intervals and testing whether the mass spectrum and spin alignments change with cosmic time. That is how an observatory comes of age. It moves from "we heard one" to "we hear them often." And then 2, they prefer these neighbourhoods at these epochs. Even our caution has become a tool for learning. The same care that models correlated magnetic murmurs, the Schumann resonances that ripple through the planet, has matured into a formal part of background searches, ensuring that when we finally pull a broadband hum from the audio band, we will know it belongs to the sky. Studies comparing site magnetometers to 3rd run limits show that correlated noise label low sensitivity then, even as they project how seriously we must treat it as instruments quiet further. Humility here is not modesty, it is calibration for ambition. When I say the closing bars of this run feel less like an ending and more like taking a deeper breath, this is what I mean. The calendar tells us that the present phase ends in mid-November and that an upgrade pause follows. The catalogue tells us we now have the statistical weight to speak of families and neighbourhoods. The multi-messenger law tells us where to look for color when gravity sings in a key that promises light. Put together, they make a promise the next phrase will not only add notes, it will resolve themes. We will learn whether the heavy high-spin tribe truly traces clusters and disks. We will narrow the stiffness of neutron, star matter until nuclear theory must choose. And we will listen with longer baselines and quieter coatings for the sea of unresolved binaries that turns from upper limit into detection, and for any stranger relic hum layered beneath it. For tonight though, let the music stay soft. The universe has been singing to us for 10 years, and we have learned the patience to hear pattern as well as surprise. In the next stretch, I want to let that patience widen into time beyond single events and catalogues toward a cosmic chronology. How these waves let us read star formation histories and metallicity across eras. How standard sirens make a map of expansion, and how, if we are lucky, the background itself will become a memory of the first fractions of a second, still trembling on the line. Let me widen the frame as promised from a single night to a cosmic diary. Gravitational waves let us read time not just as a sequence of detections, but as history written in rate. Each merger you and I hear is a delayed echo of star formation. Massive stars are born, live briefly, leave compact remnants, and only after some waiting, what theorists call a delay time, do those remnants spiral together and sing. So when we plot how often mergers happen at different epochs, we are really overlaying three intertwined stories: the universe's star formation rhythm, its chemical enrichment, and the distribution of delays from birth to marriage. That is what makes population inference feel like archaeology with a metronome. In the third catalogue, the collaborations showed that the black hole merger rate rises with redshift in step with the known crest of star formation higher in the past than today, and it did so in language careful enough to be testable as the catalogue grows. Star formation itself is now a chart we can hum, a gentle climb from the earliest galaxies, a swelling to a cosmic noon, a few billion years after the Big Bang, then a long fade toward the present. The classic review by Piero Madao and Mark Dickinson set that melody a decade ago, gathering ultraviolet light, infrared dust glow, and radio whispers into one curve. Our waves do not measure that curve directly, rather they convolve it with the physics of compact binaries. But when our inferred merger rate echoes the same rise and fall shifted by the typical delays, it is a satisfying rhyme between light and gravity. Delay times matter because they are clocks we cannot see. Some pairs merge quickly within tens of millions of years. Others take billions. Using earlier catalogues, Maya Fishback and Vicky Calogera showed that the data favor a healthy fraction of short delays, consistent with a distribution that leans toward merge sooner rather than later, unless you assume that only the most metal-poor stars make most of the merging black holes, in which case the clock stretches a little. The point is not a single exponent. It is the principle that merger rates are time-shifted star formation, weighted by how long binaries linger. And then there is chemistry. Metals astronomers term for every element heavier than helium-shaped stellar winds, and with them the final mass of black holes. Low metallicity means weaker winds, and all else equal heavier remnants. That is why the heaviest mergers we hear likely trace earlier, leaner epochs or special pockets of metal, poor gas. Modern modelling drives the point home. Vary the universe's chemical history within its observational uncertainties, and the predicted black hole merger rate can swing by an order of magnitude, while neutron star rates are steadier. New work goes further, replacing rule-of-thumb metallicity curves with data-driven reconstructions and showing how much the answer changes when you treat where the metals are with care. Our waves are beginning to weigh not only how many stars form, but how quickly the universe salts them with heavier elements. Put those pieces together, and the picture that emerges from the catalogue feels alive. A merger rate that climbs toward earlier times, sculpted by metal-poor birthplaces and tempered by delays, with hints that heavier, high-spin systems may trace the wilder nurseries we met earlier. The collaboration's population paper after the third run distilled that into a simple sentence. Black hole mergers were more common in the past in a way that mirrors star formation, and backed it with flexible models that allow the redshift evolution to be measured rather than assumed. It is a small miracle of the last decade that we can say such a thing on the strength of dozens upon dozens of ripples. Looking forward a step, the next generation of ears will turn that sentence into a timeline. The American Cosmic Explorer and Europe's Einstein telescope are designed to push sensitivity down in pitch and up in distance, so that nearby neutron star mergers are caught almost without exception, and black hole unions are seen back toward the universe's early metal-poor seasons. The Cosmic Explorer Horizon study paints it crisply. A third-generation network should record essentially all neutron star mergers out to around a redshift of 1 and an enormous census of black holes far beyond tight enough in position and distance to tie many to their host galaxies. With that weight of numbers, the convolution of star formation, chemistry, and delay times becomes an inference problem with answers, not just aspirations. Cosmology threads through the same fabric. A compact binary inspiral is a standard siren. The waveform tells us the distance in the language of gravity, and if we can learn the redshift through a kilonova's host galaxy, or statistically by cross-matching with galaxy catalogues, we trace the expansion. The collaborations have already used the third catalogue to place broad, honest constraints on the cosmic expansion history with current generation statistics. The point was never precision today, but a demonstration that the method works and is ready to bloom as the event count climbs. Third generation detectors promise precisely that, bloom thousands of standard sirens each year, many with host galaxies identified, pushing measurements of the Hubble expansion and its evolution from first steps to sharp tools. There is poetry in the way the frequency bands talk to one another about time. At the slowest end, galaxy-sized pulsar timing arrays have now uncovered a common, sky-wide ripple, interpreted as the background from supermassive black hole pairs, sketching how giant galaxies grow and merge over billions of years. In the millihertz, the laser triangle in space will hear those same giants in courtship one by one and map the era when galaxies assembled their cores. In the audio band we ply on Earth, we read the present and recent past of stellar remnant families. And underneath, as a wash that no single event can carry, there may be a background from all the faint binaries we do not resolve. And if nature is kind of relic from the first instance after the Big Bang, the third run limits on an isotropic background live just below some astrophysical forecasts already. They will tighten with this run's full analysis, and later with quieter instruments. If an excess appears, its spectrum will tell us whether we have measured the sea of unresolved binaries or something older and stranger. Older and stranger has a specific meaning here. The early universe could have left scars that only gravity remembers, networks of cosmic strings, first-order phase transitions as symmetries broke, even enhanced ripples from inflation. Reviews by Chiara Caprini and others lay out those possibilities and the spectral fingerprints they would leave across our bands. Ground-based interferometers constrain the high-pitch end. Future ground and space observatories together will outline a broadband spectrum where a cosmological relic, if it exists at accessible amplitudes, should draw a distinctive line. That is why a hard-won upper limit is exciting. It rules out easy versions of those stories and points the way to the parameter space that still lives. So the chronology we read in Gravitational Waves is becoming layered and legible. At the longest periods, we hear how galaxies grow their giants. In the millihertz, we will watch those giants pair off. In the audio band, we track the lives of stellar remnants, and through their rates, the universe's chemical adolescence. And beneath it all, we are learning how to listen for a relic hum that might be older than light itself. In the next part, I want to take that cosmological thread in my hands and follow one of its strands, all the way through how a single inspiral becomes a standard siren, how we attach a redshift, either by catching a glow or by matching a sky full of galaxies, and how with enough sirens, the expansion history turns from a classroom exercise into a measured map of the living universe. All right, one strand all the way through. How does a single inspiral become a ruler for the universe? First, the wave itself gives me a distance. The loudness of the note, the way the amplitude rises as the frequency sweeps upward, encodes a luminosity distance in the language of general relativity. We then pair that distance with a recession, a redshift measured in light. Bernard Schutz saw this beautiful idea decades ago, and when two neutron stars in the galaxy NGC 4993 sang together in August of the year 2017 with gamma rays. A heartbeat later, we finally did it in practice: distance from gravity, redshift from light, and a first ladder-independent H0 from one event. The collaboration's paper set H0 near 70 kilometers per second per megaparsec, with uncertainties large but gloriously clean because no distance ladder was involved. That was the birth of bright standard sirens. Turning a chirp into a distance is Bayesian craft, not magic. We fit waveform models to the data and map a full posterior over masses, spins, sky position, inclination, and distance. Then we marginalize to the parameters we need. In that posterior, the distance and the tilt of the binary's orbit are entangled. Face-on systems look louder than edge-on ones, so the inference naturally carries a degeneracy between distance and inclination. The AL inference workhorse papers laid out those degeneracies years ago. They remain a lived reality every time we estimate a siren's distance. The remedy is more information, more detectors on the sky, higher order modes in the waveform, and when we are lucky, an electromagnetic counterpart that fixes geometry. Because telescopes fade, while we think we paint the sky fast. Base to the rapid Bayesian localizer swallows times, phases and amplitudes from the network and returns a three-dimensional probability map in seconds to tens of seconds, a good enough sketch to move robotic optics. Hours later, slower samplers, the full parameter estimation runs, replace that sketch with a refined portrait, but the early map is what gets shutters open. Those maps are shipped in multi-order hill picks, so they stay small, yet sharp across regions of wildly different probability. Baseter's manuals describe the three-dimensional format we use today. When the glow is found, when there is a kilonova or a flare and a host galaxy, the rest is classical. A spectrum gives a redshift. We correct carefully for the host's peculiar motion relative to the Hubble flow, and we combine that redshift with the gravitational distance. Nearby hosts matter most for peculiar velocities, NGC. 4993's own motion had to be treated with care, because a bias of a few hundred kilometers per second can shift h0 by several units. There is a neat literature showing precisely how different smoothing choices in the local flow can bias the result, and how to fold that uncertainty into the analysis. We write those nuisances down because a clean method deserves honest error bars. Sometimes there is no glow. Most black hole unions are dark in light, but they are not useless for cosmology. The dark siren trick is to cross-match the three-dimensional sky map with a deep, well-characterized galaxy catalogue. Every plausible host contributes a redshift weighted by how compatible it is with the siren's position and distance. No single event decides, but the ensemble does. The Dark Energy Survey pioneered this with the August 2017 black hole merger. More recent analyses using multiple well-observed events have carried the method forward, and a stream of 2024 papers shows how to combine dark and bright sirens cleanly in one hierarchical inference. The machinery is growing up. Selection effects are the quiet spine of all this. We hear the loud and the nearby more readily, so the hierarchical analysis must include the probability of detection as a function of parameters. Modern codes, some of them LVK, internal. Some community learn that selection function from injections and fold it directly into the likelihood for H0 and its cousins. Clever variants even mix information from galaxy catalogues with what we already know about the compact object mass distribution to keep us from overweighting regions where our catalogues are thin. And then the universe answers back with its own nuisances. Large-scale structure weakly lenses every distant siren, magnifying or demagnifying the amplitude and masquerading as a distance shift. The usual cure is to add a lensing scatter to the distance error budget that grows with redshift. A recent round of careful papers has warned us that this sigma mu term depends on the cosmology and the resolution of the simulations used, and that we must be conservative until lensing maps sharpen. Some have explored delensing using shear maps to correct individual sirens, but the present verdict is that it will be hard and often unrewarding until surveys go deeper. For now, we budget the scatter honestly. Calibration matters in just the same way. The raw photodiode counts must be mapped to a strain with amplitude and phase uncertainties monitored in low latency and audited months later. The detailed O4 performance paper reports amplitude uncertainties on the order of a few to 10% across the band, with phase uncertainties of order 10 degrees in much of the sensitive range, and it documents how those uncertainties flow into distances. You will even find the photon calibrators in the technical appendices, auxiliary lasers pushing on mirrors to nudge them by known amounts, because the ruler has to be trusted before the cosmology can be. Why does all this care matter? Because the cosmos is arguing with itself about its present expansion rate. The microwave background read through the Planck satellite under a base lambda CD M cosmology favors 67.4 plus or minus 0.5. The local distance ladder Cepheids and type Ia supernovae, sharpened by the Hubble and Webb space telescopes, lands near 72 to 73, with impressively small internal errors. Sirens are the third road independent of both the high redshift early universe fit and the local ladder's anchors. Our first bright siren in 2017 was a proof of principle. The path forward is weight of numbers. Numbers are coming. The observing plans page is very explicit. The present C phase runs until Tuesday, the 18th of November, in the year 2025, deliberately extended to overlap with the early months of the Rubin observatory so that hosts can be found more often and faster. Already in March this year, the collaboration marked the 200th O4 candidate, and the public alerts page lists hundreds of notices across the run. The difference between one siren and dozens is the difference between a demonstration and a measurement. If the method feels almost musical, that is because it is. Gravity gives us the distance as a timbre in the note. Light, when we are lucky, gives us the recession as a pitch shift in a spectrum. Hierarchical inference gathers many such chords and fits the score of cosmic expansion. On the day the bright and dark sirens together tighten H0 to a few percent without ladders or early universe priors, we will have a new arbiter in the long argument about the speed of the present. And when third-generation detectors arrive, longer arms, colder mirrors, and earlier warnings, the siren catalogue will go from many to thousands, and the map will begin to include not just H0, but its gentle evolution with time. For tonight, that is the path from a ripple's amplitude to a distance, from a galaxy's spectrum to a redshift, from one event's broad stripe to a population's precise curve. In the next part, let me keep the cosmology thread, but widen it into a conversation with time itself, how sirens across redshift trace star formation and metallicity, how they will let us test not just a single number, but the way expansion changes, and why the end of this run, precisely when it falls, is the perfect bridge to the era when these measurements become routine. Night draws in, and I find myself thinking about first notes and last glances. A decade ago, in the early hours of a September morning in the year 2015, two long corridors of laser light in Washington State and Louisiana trembled in the same way at almost the same moment. That rising syllable, less than the span of a single breath, would become the first confirmed direct detection of a gravitational wave and the first sighting of a binary black hole merger. An idea that had lived for a century in equations suddenly walked into the lab and said quite calmly, "I am real." Now the room is quieter and the listening is steadier. The current observing season, what we have called Observing Run 4, in its C phase, has been extended on purpose, and it is scheduled to rest on Tuesday, the 18th of November in the year 2025. After that date, the instruments will sleep for a while, not out of fatigue, but to gather themselves to be retuned and made gentler and more sure before they open their ears again in the middle of the year 2026. I like that clarity. A pause is not an ending. It is a breath between phrases in a long piece of music. And what a phrase this has been. Earlier in the year, the collaboration marked a quiet milestone. More than 200 candidates logged during this single extended run alone. More than 200 distinct moments when the geometry of space and time brushed our mirrors, left a curve we could read. The number matters not because it is large, but because it is enough to trace families and histories, enough to turn single areas into a chorus with harmonies we can now name. The extension into November had a simple human reason to listen together with new eyes on the sky. Wide-field surveys, most notably the Vera C, Rubin Observatory's early operations beginning around October of this year, promise a new cadence of alerts in light. Extending this season by 6 weeks lets gravity and light overlap more richly, so that when the next nearby neutron star pair begins, its long, soft approach, telescopes will already be awake and facing the right patch of darkness. That decision was not logistics, it was philosophy. It said, let us hear and see at once because the universe is generous when we work together. But for now, here, at the edge of night, I want to set the instruments down gently and listen to the room itself, the quiet in which all of this becomes possible. There is a ritual to ending a day among mirrors. You glance along the evacuated corridors and imagine the photons still ticking through their long loops. You think of the test masses hanging as if asleep, isolated from the ground, by engineering as careful as any watchmaker's spring. You remember that somewhere far away, truly far, two remnants might even now be turning toward one another, and that the wave they will weave is already on its way. And you allow simply that you may or may not be the one awake when it arrives. There is comfort in that humility. The listening is larger than any of us. If this decade has taught me anything, it is that the universe is not silent. It carries memory in waves, and each wave is a story told once and never again, a last orbit, a final embrace, a newborn horizon singing its dying tones. We have learned to turn those stories into knowledge, masses and spins, histories and environments, clocks for cosmic expansion, and most wondrous to me, maps of where the elements in our rings and our circuits were made. But we have also learned something quieter. We have learned to doubt well, to measure carefully, to retract when the Earth's own murmurs pretend to be the sky, to write down our thresholds and our latencies and our errors as tenderly as we write down our discoveries. That discipline is a kind of love, really. It is how you treat a song you wish to hear again. The calendar too becomes part of the music. We know the run closes in mid-November. We know the instruments will rest. We know that next year will bring deeper, quiet, and longer reach. We know, because we write these things down in public, that plans beyond mid-year are being shaped in conversation with partners across continents, and that the door we opened 10 years ago will not be closed, only hinged for a moment, while the room is made ready for more listening. I am fond of that image, the door half open, the corridor dim, the mirrors waiting, so let the curtain fall softly. Let the last words tonight be simple ones, because the subject is large enough to carry them. We learn to listen to space. It has not stopped singing. In the early days there was a single bright chirp. Now there is weather, a moving sky of motions. We have heard hundreds of dances and found within them families. We have caught one union of neutron stars and watched its light bloom. We have set limits on a background hum and glimpsed it at far lower pitch across our galaxy with clocks. We have made rulers from melodies and weighed the stiffness of matter from the bend of a note. And we have shared what we learned quickly and openly, not because speed is glamorous, but because wonder likes company. Tonight, if you step outside, the darkness over your head will look exactly as it always has. A scattering of stars, a hint of the Milky Way. If the air is dry and the lights are few, there will be no sign that the fabric between those lights is trembling, that across unimaginable rooms, black holes are finishing their slow, beautiful work. But it is, and they are. Somewhere in the quiet, two remnants are drawing in their last circles. Somewhere else, a young pulsar is keeping time against a background so long and low, you would need 1,000,000 years to hum along. And in a handful of sleeping buildings on Earth, mirrors hang and lasers whisper, waiting for the next line in the score.